Hi everyone. In section 5.8, we're going to talk about modeling real world situations. And it's basically taking data and coming up with equations that model the data. Sometimes the data will fit a nice line and a line would fit it. Sometimes it doesn't. Sometimes you're going to get a nice general curve and a quadratic would be a better fit. Sometimes the data will just go a slope up and down, and so you'd want a cubic or even a quartic. What kind of polynomial would best model these points? And if you plotted them on the point, how would you even know which one to use? This section really is going to make a lot of use of a graphing calculator. Sorry for the rest of you. I have one I'm willing to let you borrow so you can try it out with mine, and other classmates hopefully have them as well. Or you can try an online, download a Desmos app or something and use your phone. That's fine with me to try this kind of stuff. But in any case, we're going to look at how to determine what kind of polynomial would best fit the data, and then what would that polynomial be? Could you come up with the correct equation, which is pretty cool to think about. All right, to begin with, the first thing is this n+1 principle that the book talks about, which is really helpful. The n is the degree. So if you have the degree, like let's say a linear equation, okay, so y equals mx plus b. So our degree in this case is 1. So 1 plus 1 is 2. Which basically says any 2 points determine a line. Well, you knew that, right? That's the n1 principle. So if we have a quadratic, which has an x squared, then the n would be 2. 2 plus 1 is 3. Any 3 points determine a parabola. Works every time, etc. And then cubic, and for x cubed, any 4 points would determine a cubic. Any 5 points would determine a quartic. Any 6 points could determine a quintic, as long as these points aren't collinear. They cannot be collinear. So just like 2 points determine a line, that whole progression continues up and up with different polynomials. So it's the degree plus 1 more is the number of points or ordered pairs that you would need to come up with that equation. Non-linear points. Non-linear points. If all the points were in a straight line, you're not going to come up with a cubic or something. Okay? Okay, so here are 4 points on the board, and we want to know what size, what polynomial would best model this data of 4 points. And they are not collinear. They're definitely not collinear. So since I have 4 points, it's quite possible that a third degree cubic would fit this data. So to try to figure this out on your own by hand, pre-calculator days, what you would do is you would look at the basic form of a cubic, which is ax cubed plus bx squared plus cx plus d, and look at each one of these ordered pairs one at a time and plug them in. Let me show you with just the first one. Like in this first one, when x is 0, y is -3. So this would be -3, and -3 equals, well, since all of my x's are 0, that really helps. I just have d. So d is -3. So that tells me at least, actually, 1 term of my cubic. But you would do that for each one. So you would make -1 equals 1a plus 1b plus c plus d. 5 equals, and if this is 2, then that would be 8a plus 4b plus 2c plus d. And we know d is -3, and etc. And you would do that for all 4, and you would try to put them together, and it would be exceedingly challenging to do. So we're not going to do that. Instead, because we're up to 4 equations with 4 variables, that's just more than we're going to tackle. 3 with 3 will do, but not 4 with 4. So in this case, you would put the data in a graphing calculator and you would use cubic regression. So, and that's there, cube reg, which means cubic regression, and it would give you your equation. Just like we used linear regression earlier, cubic regression will do the same thing. You can get your graphing calculator to give the correlation coefficient, which tells you how close these points fit a cubic pattern, and that's often the R squared, and if it's a positive 1, then that means it fits it perfectly. Since there's 4 points, it probably will, and it'll tell you what A, B, C, and D are and give you your equation, which is really super handy. Okay, here's the example that we have in the book of a real-world situation. This regards the state of Wisconsin and the amount of milk that was produced by that state. In 1955, the state produced 16.5 billion pounds of milk. In the year 1980, 22.4 billion pounds of milk. And in the year 2005, 22.9 billion pounds of milk. Now, fortunately, the book says what linear model fits this data, and could you use that to estimate the production in the year 2000? So you could enter in those 3 ordered pairs into your calculator and use linear regression. Or if you want to, you can plot the points and do a line of best fit. If you use the calculator and you pick 55 and 80 for these years, don't pick 05, pick 105, because that would give you the right relationship between the years. So 55, 80, and 105 for your years, and then these numbers for your y's, and hit lin reg. Now these points will not make an exact line. And if you tried to graph it and see it, you would see that when you get the correlation coefficient, it's not exactly 1, but it would still give you a linear regression. And you could still then use that to estimate at the year 2000. In this case, that would be 100 for how we would enter that in. And that's all you have to do. Now the question is, because there's 3 points, what kind of model would fit this perfectly? And because there's 3 points, it's a second degree or a quadratic. And in fact, the quadratic would fit those points absolutely perfectly because they aren't a straight line. There is a kind of a curve down. But think about realistically in life, would a quadratic best model milk production in Wisconsin? Well, only if Wisconsin was just totally bombed out or something like that. Otherwise, we wouldn't expect it in a normal world. We wouldn't expect it to go up and then all the way back down. A line would make more sense. Even if it doesn't make a straight line, we would expect it to gradually increase more and more, just like it has done. And so a linear model does make more sense in this situation. All right, our next exercise in the textbook, gives us data on cheese consumption. So this is in America, I believe. This is the year, and this is the pounds of cheese consumed per person over the entire year. So back in 1910, the average person ate 4 pounds of cheese over the whole year on average. By 2001, that had increased to 30 pounds per person. So the instructions are to take this data, put this in your calculator, and then use a cubic regression to find a cubic function to model this data. So we're going to model it like a cubic function, which kind of looks like this. That's what we're expecting this data to look like, and it does. It grows slowly and then a lot faster, right? So model that data, and then what we're going to do is we're going to use that data to estimate some cheese consumptions in some certain years. So after you have your equation, which I'm not going to write on the board, it's in your book anyway, hopefully you have your book with you, then you can estimate what would the consumption be in 1980, in the year 2000, and in 2012. Okay, what we're doing when we come up with this model is we're using it to interpolate or extrapolate. So an interpolation is an estimate regarding something within the data. So if you look, the data that we have goes from 1910 to 2001. So 1980 is within that time span. That would be an interpolation, that guess, and that was 12.6. The year 2000 is also within our data, so it's another interpolation, and that came out to be in this model, this equation that we came up with, 29.4 pounds per person. 2012 is beyond the data. That's an extrapolation. So we are going outside beyond the terms, and we're going to extrapolate from this that it would be 46.2 pounds per person. By the way, in COVID things, that's what a lot of these computer models are doing. They're extrapolating, they're taking the data they have and extrapolating some other data and what they expect, and then they're determining how we live because of that. So this has real relevance to us. In any case, these are the things that we came up with: 2 interpolations, 1 extrapolation. Which one would you have the least confidence in? And it should be obvious, not just because of the numbers, but this one you would be the least sure about. These are inside the data. They fit the trend really well. 29.4 in 2000 is really close to 30 in 2001. That just makes sense. 12.6 in here in 1980 also just makes sense. Those are logical. But 46.2, remember that graph I drew and how it just shoots up really high at the end? I would not be so sure about that one, and I hope it's not true. That's an awful lot of cheese. That's almost 4 pounds a month. That's a pound a week. A pound a week per person? Oh my goodness, that's a lot of cheese. Anyway, that's what interpolation and extrapolation, what those terms mean. Okay, I hope you've been following along. What I'd love for you to do for your lesson check, if you are able to, if you have a calculator and can, is I'd like you to take this same data here, and I want you to use your linear regression on your calculator. So scientific calculators can do this as well. Find the linear regression from that, and then use that to estimate the same 3 years. And come back and tell me what you got for those 3 years, and which do you have confidence in and which not. And look at how a linear model would differ from a cubic model. So that's your lesson check, and I will see you guys next time.